Anupji, in the spirit of time, shall we start as participants are, because you are also very busy. So we'll start now. I am putting the thing on recording.
Sir, whatever you say, I can do that, sir.
Yeah, and I have also sent messages for the participants to join.
Okay.
So yeah, they were here till 4 p.m. in the
Okay.
previous session. In between, there was a gap.
Okay. Okay.
Yeah, okay. So uh, good evening, everyone. So today we have amongst us a very prolific researcher from IIT Patna, Professor Anup Kumar Keshri. He is an associate professor in the Department of Metallurgical and Materials Engineering at IIT Patna, and he has a prior industrial experience in Bharat Heavy Electrical Limited, where he was part of the Center for Nanotechnology Group. Besides this, he also spent some time at Vellore Institute of Technology before eventually joining IIT Patna. He did his PhD from like Florida International University, Miami, in the Material Science and Engineering department, and also worked for a postdoctoral stint there till March 2011, like after which he shifted to VIT, if I'm right. So he has a very high H index, considering like the number of years he has spent in research. He's leading several very high value projects, and he has been uh, kind of cited in places like the HMS Harvard magazine for a cheaper method for graphene production. Like besides that, ACS also recognized his work besides several other organizations. So Professor Keshri, like we would hand it over to you. Thank you.
Thank you so much, sir. So I hope you are able to hear me, right? All of you are able to hear me?
Yes, yes,
Yes.
loud and clear.
Yes. Yeah. So nice. So very first, I would like to thank the organizer for giving me this opportunity, and thank you so much, Professor Thakur, for your kind words. So now let me start talking about the title directly about the plasma spraying beyond traditional coatings. I'm sure that some of you might be knowing this or some of you might not be knowing about this, but no worry, because I'm going to start from the basics of the plasma spraying and beyond traditional coatings. Basically, what we can do with the coatings and what is that title stands for, that is beyond traditional coatings. Right. So before I jump to the directly onto the topic, I'm going to give you the little bit glimpse about our group and about our group and our group activity. So this will be the very brief about our groups, and then we are going to talk about directly onto the plasma spraying. So now, so let me change the slides now. So now, before I go ahead, so I have to must thanks to all my, hardworking students who is just behind all of this work, and I'm just presenting in front of you. So now these are the you can see that the students, that 4 PhD students and around 23 master students have been graduated from this group, and right now the 10 PhDs ongoing and 4-5 masters are ongoing. I must thanks to all of our funders who is giving the continuous support to the plasma spray coating laboratory, and which you can see here, that is IIT Patna, ISRO, DST, Imprint, BRNS, DRDO, CPRI, Tata Steel, Carborundum, as well as Plasmatron. So now, apart from this now, so I have to also give the humble tribute to the Biswajyoti Mukherjee. Just now, Professor Thakur was telling about some of our work has been highlighted in the CNN News and Harvard University. This was the student who was behind this work. So this I'm going to show you that what he has done this, and I'm just presenting about his work here now. So he has left us during the second wave of the COVID. Now, so about our activities, basically our laboratory is plasma spray coating lab, and what exactly we do here. So when we talk about the traditional coating, right? Traditional coating means It's all about the making the wear and corrosion resistance coating, because if we try to see the literature, then plasma spraying is not a new thing, and people are already using this from last for 50 to 60 years. And basically there are, if we try to search the workshop of plasma spray in India, there are more than hundreds of workshop will be there into the entire India itself only, which will be dealing with the wear and corrosion resistance coating, right? So then that is what we, our title says, that plasma spraying beyond traditional coating, right? So we are definitely working onto the wear and corrosion resistance coating, but we are trying to take the plasma spraying to a different level now. So in this we can see, you can see here, that is we are trying to make the nitride coatings by the plasma spraying, where people they try to make it by the CVD or the PVD technology. Now, this is again, I'm going to show you the tailoring the wettability of the coating. I'm going to show you some video also of the coating, what exactly we did here. So wettability of the coating means we have changed the complete, surface morphology of the coating, and then we have made the different kinds of the entire wettability difference. That is, it should show the hydrophobicity, hydrophilicity, and entire range of that. And apart from this plasma spray coating laboratory, we have recently done the graphene coating, as well as we synthesize the graphene powder too, right? So this was the advancement which I really wanted to emphasize in this presentation, and I'll be showing you some of the exciting results which we have got it here. Now in the right hand side you can see the list of the projects which we have already completed, or some of them are ongoing. So now let me go on to the next slide now. So I have to little emphasize onto this, because recently our laboratory has got the, grant of for creating the Center of Excellence at IIT Patna in the wear and coordination coating. And this grant we have received for the 5.78 crores. In this, IIT Patna is the coordinating institute, and our other institutes are NIT Patna, AIMS Patna, IIT Dhanbad, CMRI Durgapur, and our industry partners are Applied Materials, Tata Steel, and Associated Plasmaton Private Limited. So now this is the work which I was trying to show you here. This has about the making the graphene powder by the plasma spray. So this work has been published in a highly reputed journal, and now when this work has come out, this has gone to the Harvard University, which has been highlighted that is a cheaper method for graphene production. And this is also I wanted to show you here, that is it has gone to the CNN news highlighted by the ACS magazine. Then it is Harvard University. Then you can see here, this is the week magazine, which is our national magazine. Then it has been highlighted by the American Ceramic Society. It was also highlighted by the Graphene Council, where Professor James Tour from Rice University and Professor Cecilia Matevi from Imperial College of London has acknowledged our work, and said about that it has the potential for the commercialization. So this was a little about the activity of our group and about what exactly we do that. Now let me directly come to the topic. What exactly is plasma spray coating? So very first, let me make you understand what is plasma spray, and then we'll go on to the showing you the result. So basically the word plasma, you understand, this is the fourth state of the matter. And when the word plasma is coming, it means that it will be having the higher heat when we talk about the DC plasma. Right now, plasma spray coating means we are trying to utilize the plasma for melting the high melting point, powder particles. Now, so when we talk about the high melting point powder particles, means it must include the ceramic particle, right? So, or ceramic powder. Ceramic powder, if we try to see that, which is very much commonly available, is the aluminum oxide. It is cheaply available and much abundant in this earth. So aluminum oxide melting point, if we try to see that, it is having around 2060 degrees centigrade, right? And if we try to talk about zirconia, then it is having the melting point of around 2700 degrees centigrade. We talk about silicon nitride around then 3200, tantalum carbide around 4000 degrees centigrade, right? Now, so when we are talking about these high temperature materials, then we really need some kind of the source to melt this powder particle, right? So once we melt the powder particle, then we will try to do the resolidification over the substrate and making the coating over there. So basically, what is we are trying to do that we are trying to make the inert coating over the substrate. Suppose if our substrate is metallic substrate and this metallic substrate is being exposed into the seawater or at the high temperature. So we know that this, if we expose it at the high temperature, our metallic substrate will get oxidized, or if it will be exposed in the seawater, it will get corrode. So what we do that we try to make some kind of the ceramic coating which is inert towards the seawater, or it is also inert towards the acidic attack, and also it is much stable at higher temperature. So that is why we use the ceramic powder coating over the metallic substrate to completely laminate the substrate and making this substrate as a much as a protection with this coating, right? So now this you are seeing in the extreme right hand side, that is the substrate which you are seeing here. This substrate could be of a like the metallic substrate, and over the metallic substrate, now let me show you the small animation. These are the powder particle, means we procure the ceramic powder particle from outside. This ceramic powder particle we procure it as per our needs, means what about the coatings we have to make. And this ceramic powder particle, it gets completely melted in the plasma, and once it melts, then we accelerate it towards the substrate where it bombards over the substrate, and then you can see that it flattens over the substrate this spherical powder particle which will be flattened over the substrate, and then it will get resolidified. So then you can see that this process is like called as layer by layer deposition. So this is, you can see that layer 1 has been deposited, and now you can see that there are multiple layers are keep on depositing. So these individual layers is called as splat, single splat, and now the multiple layer by layer deposition is known as your coating. Now the thickness of this coating is completely depends upon the application, whether we wanted to use this coating for the corrosive environment or for the oxidation or for the tribological property, right? Based upon that, we keep on manipulating the coating thickness. But I hope now you are able to correlate about what is the plasma spray coatings. And now if we try to show you, this is the rough schematic of the plasma spray coating, where you can see that there are a lot of the heterogeneities are involved in terms of when we are dealing with the high temperature melting of the powder particle, then it must be having some kind of unmelted powder particle. It must be having some kind of the voids, or it must be having some kind of the oxide inclusions, right? So if these that many kinds of the unmelted powder particles, oxides, voids are there, then our coating is very much heterogeneous, and the property will be differing very much from the one to different directions. So what exactly we do that here now? So this is what we do that here. We try to completely make the coating as a uniform properties. How will be doing that? So now let us see here in the plasma spray technique. Now if we try to talk about the what is the major novelty or the uniqueness of this technique. So uniqueness of this technique, you can see it is an extremely high cooling rate, and so we can see that extremely high cooling rate means 10 to the power 6 or 1 million Kelvin per second. So now when we talk about that much of the high quenching rate, so that is why the chances of the oxidation of the powder particle at high temperature is very minimum, because yes, temperature is involved, but the plasma exposure time is in the microsecond. So that is why sometime plasma spray is also best suited for making the nanoparticles, because we know that whenever we talk about the thermodynamics, the reaction to complete, we really need the kinetics too. So here temperature is very high, however the kinetics part is completely missing, and that is why our reaction is not being able to carry forward, and that is why we get the very less corrosive oxidation product into the melting. Now here you can see this is our plasma gun at the bottom, and in that you can see the dotted line, that this dotted rectangle is showing the, some kind of the shroud means we have made it customized. And in this what we do that, even if some materials are very prone towards oxidation, and we know that if we are exposing it at high temperature, then there is a high chance that it will get oxidized. So for the safer side, we also pass the inert atmosphere, we pass the inert gases when we try to make the coating into the substrate. So basically this inert shroud cut down the exposure of the molten powder particle from the environment. Right now, this is the fishbone diagram which you are able to see here, the fishbone diagram. Now this fishbone diagram, it is showing the here the coatings property. Right now, when we talk about the coatings property, coatings, this will be having the mechanical property like manipulating the hardness, elastic modulus, toughness. Right, we can also think about the thermal property like coefficient of thermal expansion, then its thermal stability, then thermal conductivity. Right, so there will be a lot of the different kinds of the coatings property. Now, when we try to see that if the coatings property, then how can we manipulate the coatings property? Now, so there are major part is like process variable, powder characteristics, substrate condition, spray equipment. Right, so there are multiple parameters are there, and under all this there are under process variable we can see plasma power, gas enthalpy, heat transfer, primary gas flow rate, stand up. There are multiple of the parameters are there, and at this point we are not sure that which parameter is impacting onto the which coatings property. Right, so our expertise lies in creating the process sheet for all the different kinds of the coatings. Suppose if we wanted to make the coatings for thermal barrier coatings for the turbine application, so we know that what should be the coatings property and what kind of parameters which we have to really manipulate, and how it will translate the coatings property. So that is what exactly we are keep on doing that from this entire list of the process parameter. Right, so now let me show it to you some of the exciting results which we were talking about, initially. So I'm going to show you one of our work, and that is about the ultra fast mass production of high quality exfoliated graphene. Right, so when we started this work, then we never thought of that, that it will be going, we will be able to get that much of the success, because when we talk about the graphene and when we talk about the plasma, these are the two extreme end. Right, because plasma will be having the temperature of more than 2000 degrees centigrade just at the periphery of the plasma, and we know that when we talk about the graphene, it will get oxidized at around 400 degrees centigrade, so we will not get anything. And now what we are talking about, making the graphene powder using the plasma spray. Right, now, why this idea has come to our mind, that is, we thought of that there are several techniques are there for making the graphene. There are several and several, right? And in that, the best technique which is known so far is by the CVD technique, because it gives a very high purity graphene, right? Single layer high purity graphene for a large scale. So we thought of, right, that is how can we make the graphene powder by the plasma spray. Now we thought of that is, we know that in the graphite, these are the between the layers there is a van der Waals force, and if we try to somehow try to exfoliate this single layer from the graphite, then it will be very easy for us to make the powder through the plasma spray. Now the idea behind was that is, if because plasma can give the high temperature, so thermal shock it can give. Thermal shock means at the very high temperature, but the quenching rate is so high, so my powder particle may not get oxidized because our quenching rate is so high. Right, and then after this, once it get completely the bond between them, between the layers gets weakened, then what we do that we completely give the acceleration towards the powder chamber, where it will completely get disintegrate. This was our idea, and now let me show it to you that how we proceeded and what we got it. So from this now, from the plasma spraying, the graphene which we have got it after doing the, multiple of the analysis, we have found that the single layer selectivity, single layer was around 85% in the single layer. Basal defect free, that is the basal plane was having no defect at all. That is why we are talking about ID by Ig ratio is 0. It was having the high purity carbon by oxygen ratio 21.2 and sp2 content was around 95%. So if we try to see the carbon by oxygen ratio, it is comparable with the CVD technique, which we have already reported in our work. And plasma spraying, we know that it is having the very high production rate because it is having the industrial application. So now I'm going to show you that how did we start the whole work and how did it landed. So basically, first in the left hand side, you can see the synthetic graphite which we procured from the Sigma Aldrich. Now synthetic graphite is not very costly. We can say that here in around 12 to 15,000 rupees, we have got around 3 kgs of the graphite. Right now, so we did the multiple of the experimentation to understand about the initial phases and about the morphology of the synthetic graphite from the Sigma Aldrich, which you can see here left hand side, that is by the clearly you can see by the X-ray diffraction, then the SCM, then the TEM, then the BT surface area. We understood about what is the initial surface area of the graphite, right? So once we are having all the required data of the initial synthetic graphite powder, then we started, pouring this powder or feeding this powder into the plasma spray. Right, in the plasma spray, basically at the high, we tried to put it at the high temperature, but we have definitely put it the shroud there also in the plasma. Right now, once we have, once we sprayed the powder particle, we kept the powder chamber on the other way, and then we collected the all the powders after the spraying. Once we collected the powder, then you can see the image A, that is what in the right hand side, which you can see that there are much of the powder we have just got it in this bottles, you can see that. And now after this, we thought of that it may contain the exfoliated graphene, and with that intention we started doing the experimentation onto this. So our first experimentation was the bottle B and C, which you are seeing that is we are trying to disperse it into the DMF and NMP solution. And what we found that after the 24 hours of the dispersion, powder is still completely dispersed in this. So then we thought of that, yes, it definitely might have been exfoliated, that it's indicating. Then after that, image D, which you are seeing here, that is the X-ray diffraction image, right? X-ray diffraction. And in this, what you can see that here, this is the blue one is for the graphite and the red one is the exfoliated graphene. What we can found it out from these two, the sharp decrease in the intensity of the exfoliated graphene. And please mark it here in the Y scale. It is not an arbitrary unit. It is intensity actual what we got it from the instrument. So the sharp decrease in intensity means definitely the exfoliation has been taken place. But so after this, what we have done that image number E, if you come to, that is a Raman spectroscopy image of the graphite and the exfoliated graphene. So graphite was showing that is a D and G peak, which is the characteristics of the graphite or the carbonaceous material having at 1350 and 1550. And then around 2700 degrees centigrade, 2700 per centimeter, that is the 2D peak, right? So now we can see that for the exfoliated graphene also we are getting the similar kind of the signature, and to our surprise what we got it, the 2D peak, that is the much higher intensity into the exfoliated graphene, which is the representation of the very high purity graphene into this. Now image F, which you can see here, image F, this is the transparent flake of the graphene onto this. But right now we are not sure whether it is a single layer graphene or multiple layer graphene or bilayer graphene. So but these figures what you are seeing here, A, B, C, D, E, F, and G that is the surface area. When we measure the BET surface area, then surface area it is showing here 780 meter square per gram. And initial surface area of the synthetic graphite was less than 1 meter square per gram. So this is the definitely the indication of the that exfoliation must have been taken place, right? So this was our initial investigation onto the powders which we received after the exfoliation. Now after that we started going much inside of this powder particle, right? Now the left hand side, if you try to come onto this, these are the, these are the much in a investigation by the HRTEM, and image A, you are seeing that it is the low magnification image. And what we found it is a very transparent flake, which you can see over the copper grit, right? You can see here. And image B, you can also find it out the little higher magnification image, and the arrow mark, if you try to follow, then it is showing here some kind of the transparent flake. It is here, though it is not quite visible because it's we are believing it is a single layer. But when we do the again the further high resolution images, the C, you can see that the single layer image, this is single layer because there is no any visible any edge lines. You are seeing that here. After that we have done the fast Fourier transformed image onto this, and then the image D, and you are getting it here, the complete hexagon we are able to see for the single layer graphene. The image E, which you are seeing here, this is the SADP pattern collected from this image C, and then the intensity of the place we have plotted it, which is completely matching with the single layer. Now similarly F, G and H, if you try to see the image H, it is showing, if you compare the image C, H and M just below that, so you can find it out the layers which is looks visible. This is single layer, then the two layer, you can see the two lines onto the edges, and at the bottom you can see the three layers, right? And even if now you try to place the two layers, then you will be finding it out from the top hexagon has changed into the rectangular one, which you are able to see. And when you will try to place the three layer, it becomes the triangular onto this. So that is what you are able to see here, right? And if you try to see the SADP pattern, the single layer was having the intensity higher in the two middle peaks, but the multiple layer, that is the two layer and three layer, is having the higher intensity at the both corner of the planes. So this is the visual observation which has reflected that it is having the single layer, bilayer and tri-layer. But we are not sure at this point, that is how much percentage is the single layer, how much percentage is the two layer and the three layer. For understanding this, what we have done the exhaustive analysis onto the AFM. Now you can see the right hand side image P, and in this you can see that AFM imaging of this powder particle, and all the flakes which you are seeing, that along this dotted line in the AFM we have plotted the thickness profile, and you can see the thickness profile, that is Q, the line where it is passing the 0.8 nanometer, 0.9 nanometer, 1.2 and 0.6 nanometer. These are the flake thickness, which is definitely considering at it is a single layer onto this. Now we have analyzed now in the image R, which you are able to see image R, that is the flake thickness and the count frequency. We have analyzed around 3 to 400 of the flakes, and then what we found that most of the flakes are less than 0.9 nanometer, right? And then you can see the second layer and the third layer. When we have taken this frequency chart, then what we have concluded, that is around 85% of the our flakes, that is around out of 400, around the more than 330 flakes was around 0.9 nanometer. That is why we have reported here that is it is having the 85% of the single layer. Now the flake size, if you try to see the lateral flake size, then it is coming from 0.8 to 2.8 micron. And here the image T, it is showing that is about the FESEM images of the flakes. So what we have showed from the AFM, then we tried correlated with the how our flakes index looks like in the SCM. So here also you can see that, and which is completely correlating all our entire work. Now, so once we understood about the how does it looks like and what is the percentage, now it is we thought of, let us try to go ahead, that is how we can say that single layer and the quality of this, graphene production what we have done. That the top images which you can see here, that is the image A, that is the Raman shift versus intensity count, and you can see here this has been plotted for the graphite 1 layer, 2 layer, 3 layer. Now in the 1 layer, what you can see, the complete symmetric peak, right? Complete symmetric peak, which you can find it out around 2700, right? And if this is the complete symmetric peak without any kind of the splitting onto that, it is the clear example of the single layer. When there is some kind of the splitting in the peak is happening, then it will be the 2 layer, 3 layer, and the graphite which you are able to see here. Now from this, when we claimed that it is having the basal defect free, right? Basal defect free means that is what we have done, that we have done the experiment over the clubbing the Raman and the AFM together. So you can see here the image B and C, it is the Raman, it is the AFM flake. And once we have captured this under the AFM, then we have taken the Raman intensity at the center of this flake, and as well as at the edges of this flake. So center of the flake, when we are taking it here, then you can see the image D, which is the basal plane of the flake. That intensity is going very high in the G, and there is absence of D peak, which is showing that our basal plane does not have the impurity. And when we are taking the image E from the edges, so you can see that the image, that is the peak is coming, the D peak is coming. So what we can conclude from this analysis, that is the edges contents of around the some impurity ID by Ig equal to 0.2. However, the basal plane does not have any kind of the defect. Right now, when we have done with the about the quality of this our graphene, then we have done the very all the XPS analysis at the bottom, which you can see that is the XPS analysis onto that. And if you can see the series of the low scan images and the F, G, and H. So G, you can see that there is a presence of the CC bond, C double O bond, and the pi pi bond. And using this, integrated over the area, we have calculated the carbon by oxygen ratio. Now, when we compared this with the literature, then in the H, which you can see that here sp2 percentage with the carbon percentage. So you can see here the CVD one, it is the green one, which you can see that it is touching, our present work is touching the CVD one, right? So that is what we are talking about, that our graphene produced the carbon by oxygen ratio is also coming near to that. That is around 95% of that. Right now, after once we have confirmed the about this about the purity, the quality, then about the single layer percentage, then we thought of showing the complete the proof of concept of this our graphene produced. So what we have done, we have done the multiple proof of concept, which you are seeing it here. Now the first one which you are seeing here, we have tried indenting over the single layer, 2 layer, 3 layer. This was a very sophisticated characterization carried by the AFM at IIT Kanpur. And we have nicely, dispersed the AFM over the pillar. Over the pillar means we have taken the substrate, and over that we tried putting it out, and then we tried doing the indentation over there. We have put the supplementary file and detailing all the experiments. How did we do this? With all the microscopic images. So in this you can see that how the our force versus indentation depth is moving, and then from there the single layer has coming the Young's modulus of around 860 GPa, and the layer 2 is 645, layer 3 is 550. Then we have done the load versus, that is the coefficient of friction, that is the tribological test. We have done that, how the coefficient of friction it is matching. So then you can see the graphene coated over the silicon substrate, the coefficient of friction drastically reduces, coming towards 0.0, around, it must be around 0.01, something like that. But uncoated black one, we can see that the coefficient of friction is around 0.4, right? Then we know that graphene is having the very high thermal and electrical conductivity. So what we have done, that we applied the voltage for the range of the voltage and try seeing that how the current it is going on with our graphene, right? So this blue one is for the substrate, and the layer, you can see layer 1, 2, 3, right? And then we tried doing that. We can see here layer 1, the red one, is for very small range of the voltage, how the current is shooting up. But for the little higher for the layer 2, 3. So we did the various, then again, electrochemical study also about that, to understand about the GCD curve and the CV curve. And then we found that our graphene is showing the property which is having the graphene produced by other techniques like the ball milling, by the CVD techniques and all. So this was the proof of concept which we have produced. So this entire work is giving the confidence that plasma spray technique can produce the high quality graphene, right? So this is now follow up work is also going on into this direction. But right now we are trying to do the commercialization of this with we have got the one project from the Plasmatron, and we are trying to commercialize this whole technology again for the commercialization. Now let me show it to you. Professor Thakur, how much time I'm having now? Professor Thakur? Hello?
Yeah, I have to
Yeah, I have
unmute
to unmute
myself.
myself. Yeah. How much time
So
I'm having?
you can use
You can
about
use
15 minutes.
15 minutes, right?
15.
Yeah, 15. Yeah. So sure. So I will be using the 15 minutes, then I will be stopping. Yeah. Okay. Thank you. So now let me show it to you my our other work about the, this was, we discussed about the graphene powder, but now we are trying to show you here the graphene coating, right? Now graphene coating means, you can see here, this was the different work which has been published in, again, in a good journal. And in this, which you can see here, this was the, on the top side, you can see that this is the graphene powder having the spray dried, means we really cannot spray the pristine graphene. So what did we do, that we made the ball of the agglomerates of the graphene, and into this we did the initial characterization. You can see at the bottom, high magnification, one particular spherical ball of the graphene. In the right hand side, you can see that this is the graphene coated over the glass substrate. N equals to 0 means there is a bare substrate. N equals to 1 means only the one pass we have given. N equals to 3 means there are 3 passes has been given, and N equals to 5 means 5 passes has been given, 5 layer has been deposited, right? So you can see that how the color is changing. Layer 1 is having little transparency, which is completely getting more darker and darker when N equals to, it is approaching towards the 5, right? So these are with we earlier thought of that it will be having the graphene coating, but now we have to do the analysis onto this. And once we saw under the FESEM, we found it out some, cross-sectional images showing the graphene coating. It is there, and we tried showing it, seeing that the patches under the AFM, which is showing that height profile around 320 nanometer. If we try to see that the thickness has been deposited by doing the, Raman spectroscopy, and by the HRTM analysis, we confirmed that the structure of the graphene has been retained. And then we did the analysis onto that. How did it got retained? Because of the, mainly about the inert atmosphere shroud, as well as because of the very much high quenching rate onto this. We have also done the, again here, the proof of concept in the conductive AFM. You can see here in the left hand side, the image A is the only the alumina substrate, and we know that alumina is the insulator. So that is why for entire range of the voltage, you can see current is almost 0. But here same alumina we coated over with the graphene coating, and you can see here corresponding the entire for the range of the voltage, right? So which you can see that for a small range of the voltage, current has suited up like anything here, and it has got to the saturation. So which is showing that definitely the graphene coating has been intacted, because we know that electrical conductivity of the graphene coating is very high. Now we showed here the corrosion property of the mild steel versus the graphene coated over the mild steel, right? The inset image in the right hand side, you can see here the mild steel, the corrosion rate is very high, but same mild steel, if we have coated it with the graphene, the whole corrosion rate has drastically been reduced. And so apart from this, it is giving the very good indication that corrosion property or corrosion resistance can be enhanced by just making the coating with the graphene over the mild steel. The coefficient of friction which you are able to see here, that is the graphene over the alumina substrate, and alumina substrate coated with the graphene, the coefficient of friction, how it is drastically reducing. So these all the proof of concept, it is indicating that our graphene coating has been successfully deposited, right? So this was the one work it has been done. And now let me show it to you the other work which we are talking about, the tailoring the wettability of the coating. Now tailoring the wettability of the coating means what we have done, that we have deposited the aluminum coating over the glass substrate, and what we claim that by changing the process parameter we can achieve the range of the wettability. Range of the wettability means if I wanted to make the super hydrophilic, then hydrophilic, hydrophobic or super hydrophobic, and we know the clear differences between them about the water contact angle, right? We know that if the water contact angle is greater than 150 degree, we can say it is super hydrophobic. Greater than 90 degree, it is hydrophobic. Less than 90 degree, hydrophilic, and less than 10 degree, super hydrophilic, right? So what we have done, that we have taken the aluminum, just metallic powder, and coated over the glass substrate, and changes the process parameter in such a manner that we should be seeing with the same powder, see, we should be seeing the different kinds of the hydrophobic. Now let me show you the very small video onto 30 seconds video onto this. So which you are able to see here, the four sample A, B, C, D. This is the aluminum coated over the glass substrate, and the R, it is the bare glass substrate, right? Now image A which you are able to see here, this is the digital image of the aluminum coated over A, which we claim to be the super hydrophobic, where the water contact angle is very high, more than 150. B is again hydrophobic, means greater than 90 degree but less than 150 degree. C is less than 10 degree, super hydrophilic, and D is hydrophilic, that is greater than 10 degree, less than 90 degree, and R is completely uncoated substrate. Now let me show it to you here the video. If you are able to follow this, we are putting the water onto this, so you can see the droplet of the water, how it is coming onto this substrate, right? So you can see that how the droplet, it is behaving over the glass substrate, right, over the coating. So see, you can see here the C is completely super hydrophilic, complete water has been absorbed, right? And image A, that is the super hydrophobic, right? So the differences in all this is only about the changing the process parameter in the plasma, right? So you can see that by changing the process parameter, how the water droplet is behaving onto the surface, right? So let me show it to you that again, super hydrophobic coating, where we tried continuously wetting over the glass substrate, right, which is coated with the super hydrophobic coating. We are trying to continuously wet the surface, but you can see that how it is behaving. So this is the super hydrophobic coating deposited by the plasma spray. Now let me show it to you here. The third image is here. You can see that which has been captured by the high speed camera, super hydrophilic, where the water droplet, when it is falling down over the surface, completely got adhered over the surface. But when we talk about the water droplet, it is jumping over the super hydrophobic surface. You can see that how the droplet is completely, it is just rolling over the surface, right? So this has been captured by the high speed camera. And what was our understanding, this, if this is rolling over the surface, then it may also take out, if any kind of the dirt particle will be there, it may take out the dirt particle, and hence it may behave as a self cleaning coating, right? So what we have done, that we tried measuring it out, the self cleaning coating parameter onto this, right? So let me go on to the next slide. Let me show it to you here. This is the glass substrate without any kind of the coating. We have put the some kind of the dirt here, right? Or alumina grits you can see here. And you can see how we are putting the water onto this and how it is getting cleaned. We can see here, this is not very nicely getting cleaned, right? This is not nicely getting cleaned. But when we try showing that here over the glass substrate coated by this, over the aluminum, this is super hydrophobic coating. And now let me put the water onto this. You can see here how this nicely getting cleaned, right? Which we are able to see here. So definitely what we feel here that it behaves as a self-cleaning coating. If the water droplet is falling onto this, it is taking the dirt also with them, right? So this is called as a self-cleaning coating. So we established that wettability of the coatings can be manipulated, and based upon that we have got the project from the Tata Steel Limited, and we have done the similar kind of the work for them for the iron based material, and we have filed the patent and published the paper for the Tata Steel Limited. So apart from this, now these are the complete mechanism behind this. What exactly was happening? Why did it behave like that? You can see here multiple of the characterizations we have done that, and due to the shortage of the time, I will not be able to show you all, but it has been published there, right? So basically what I let me say you in just in a few seconds that basically what we have done, that we have manipulated the the micro pillars which you are able to see on the top right hand side, A, B, C, D. That is the micro pillars which we have manipulated. You are able to see for super hydrophilic, the micro pillars are very less in quantity, right? The B is having the little higher micro pillars, C is again increased, and D is more and more higher micro pillars, right? So these micro pillars are responsible for water droplet to just hang over the surface and not to penetrate over the substrate, right? So this is what we have played, and we have found it out with the multiple of the characterization and how this makes. Apart from this, we have confirmed that it is also the robust, means at the high temperature the wettability will not go, and also when you are rubbing this with the 100 gram of the load with the emery paper, still the contact angle will be remained there. This we have proved it. But the further work of scope here, it will be here, that is it can be increased from 100 gram to the again 200 gram and up to 1 kilogram, and then we have to see what exactly is happening. This is our another work which we have done that recently, that is the making the ceramic membrane for water filtration, and our industry partner was Carborundum Universal Limited. And in this what we have done, that we have made the ceramic membrane for the water filtration for this. Now you can see here that we have made